Good morning. Let us continue our lectures. Last time we discussed possibility to make the class of Gaussian processes with respect to these processes. We can define stochastic integration. So we introduced such a notion, integrator. This is a centered Gaussian process, for example, the interval 0, 1 is centered Gaussian process such that there exists some positive constant c, that for any partition of the interval 0, 1, any real number c0, cn minus 1, and 1, we have the following inequality. The expectation of the square of k equals 0 to n minus 1, ck delta x tk square is less or equal than c sum from k equals 0 n minus 1 ck square delta tk. We have seen last time that Brownian motion, of course, is the integrator. We have even equality here with c equal to 1. Brownian bridge is integrator, and any smooth Gaussian process is integrator. Smooth in the sense that it has continuous derivative. Why we pay attention to this class of processes? Because it occurs that they generate the Gaussian random operators in the initial Hilbert space of square integrate functions. So let me use it. Now we consider as a Hilbert space for white noise L2 0, 1, and we have here white noise psi, which is generated by W dot, formal derivative of the Wiener process. Rigorously, it means that psi h is equal to the integral from 0 to 1 h w. Now I will suppose that x is jointly Gaussian. With psi. So let us note that this property gives us possibility now to define the Gaussian strong random operator with the integrator. Namely, let us consider the following function h of t, which is equal to the sum from k equals 0 to n minus 1 ck indicator of tk plus 1 from t. So this is a step function for any case. I just here is its graph, for example. Yeah. And this inequality tells us that one can define for such h of t the integral from 0 to 1 ht dxt. Naturally, it is defined as a sum from k equals 0 to n minus 1. And here we have this ck delta x. So we have such an integral. By the way, I said natural, but some of you can recall the theory of Lebesgue-Stieltjes integration and begin to ask, why I don't pay any attention to the limits from the left or limits from the right of this function. Yeah, it's the point of jumps of function ht as it is done in the Lebesgue-Stieltjes theory. The answer is following. We have the inequality for x. From this inequality, it follows that x will be Hölder continuous in square mean. And we know that for Gaussian process, Hölder continuity leads in square mean of any order, Hölder continuity in square mean leads to existence of the continuous modification. So integrator with necessity is continuous. So I have not paid any attention to the left and right limits at the point of jumps when saying naturally the integral from the step function is the following. Moreover, it occurs that if we have arbitrary function h, if we have arbitrary function h from L2 0 1, then of course I can find sequence of step functions hn is a sequence of step functions such that hn tends to h, n tends to infinity in L2 0 1, then it occurs that the integrals that there exist a limit when n tends to infinity of integrals hn dx. This limit exists in L2 sense due to the inequality from the definition of the integrator. And it is natural to define this the integral from the function h as this limit. It is trivial to check that this limit doesn't depend on the choice of the approximated sequence. Please do this as an exercise. So we have seen that the name of integrator is was done by the following reason. We can integrate against x functions from L2, 0, 1, exactly as it was with the Brownian motion, but of course here we have not equality. We have not equality, just the following properties of the obtained stochastic integral. We just have that expectation of the integral from 0 to 1 h dx equals 0, because for this random variable is true due to the fact that x is centered random process, and expectation of the second moment h dx is only less or equal than c norm h squared. I just recall that in case of Brownian motion, we have here equality with c equal to 1. But here we still have a more or less nice inequality. Okay, good. So we have such a nice property that we can use the integrator to build some kind of stochastic integral now from deterministic functions, but maybe you already expect that if we consider this integral as a Gaussian random functional or Gaussian random operator on our initial space L2, then maybe we can apply our construction and define random actions of this random functional onto random integrants here. Yes, we will do this. And you remember that we discussed description of any Gaussian strong random operator in terms of e-to-winner expansion. Here we will do the same, but it occurs that it is better to investigate firstly the structure of integrator. Then we will see that we can describe integrators easily in terms of white noise, and after this we will continue with the construction of stochastic integral with respect to integrator. So let us discuss the structure of integrators. We already have seen that there are several examples of integrators, and now let us ask what will be a general kind? What will be a general kind of integrator? And the following lemma gives you the answer. Lemma x is an integrator if and only if there exists operator A, which is linear continuous operator in L2, 0, 1, such that xt is equal to xi multiply on a from indicator of 0. Let me again read this statement. X is an integrator if and only if there exists continuous linear operator in the space 2, 0, 1, such that xt is equal to the scalar product of our white noise w dot onto this vector, which is obtained by application of A to the indicator of 0 t. So it is equal to the integral from 0 to 1 A indicator of 0 t, that we put here brackets to emphasize that we apply this operator to this function from S dws. So we have such a representation for integrators. Let's prove this statement. Sufficient. Suppose that xt has the mentioned representation. So it is like C A indicator of 0 t. Then, if we want to consider this sum, which arise in the definition of the integrator, so I will not repeat the partition, Cn, you already remember this. So we have a sum from k equals 0 to n minus 1, ck delta xtk. It will be the sum from k equals 0 to n minus 1. Here is ck, here is xi, a indicator. I just use here a difference of two indicators. One will be indicator up to tk. Another one will be indicator up to tk plus 1. The difference is the indicator of this interval, tk plus 1. So I use this here and get the following. Here is indicator tk plus 1. That's all. Now let us consider the such transformation. I just put sum inside of the scalar product. Then we will get the following. We will have xi multiplied on the a, which is applied to the sum from k equals 0 to n minus 1. Here is ck indicator of tk plus 1. And you recognize here this step function, which we already discussed. So now let me use just a riser to check its second moment. I will do this as follows. So expectation of this n square is equal due to the properties and definition of Gaussian white noise, just the norm of A applied to this step function, k equals 0 to n minus 1, ck indicator tk plus 1. Okay, norm in square. Now I'm using the fact from the lemma condition that A is continuous linear operator. So the norm of A application of A to some element is less or equal than the norm of operator A, operator's norm, multiplied on the norm of this element. So I can continue with the norm of a square multiply on the square of this norm. This is exactly the sum which arises in the definition of the integrator. This is ck square delta tk. Okay. So we see that if the process has this representation, then it is integrator. Moreover, our constant c can be defined as follows. It is exactly a square. Yeah. Okay, let's go back. So next. Necessity. Let us consider now x process x, which is already integrated. Since x is Gaussian, jointly Gaussian with psi and centered, then it has the following representation. For any t, which belongs to interval 0 to 1, there exists the function, there is the element, let's call this element by ft, belonging to L2 0, 1, such that xt is equal to psi ft. Okay. Now let's use that xt is an integrator. So let us consider the step function h, which is equal to sum from k equals 0 to n minus 1. Here is ck, and here is indicator of tk plus 1. I will define h, a from h by definition is equal to sum from k equals 0 n minus 1 ck. Here is ftk plus 1 minus ftk. Okay. We have to check that this definition is correct, but it follows from the definition of the integrator. If we consider now norm of h ah square, it can be calculated as the expectation of the application this k equals 0 to n minus 1 ck phi tk ftk plus 1 minus ftk xi, and as in square. This is just from the definition of white noise, and then it is equal to the expectation, and it is equal to the expectation of sum from k equal 0 to n minus 1. Here is ck delta x tk by definition of ft square. It is less or equal than, I will finish this with c norm of h square. Yeah. So we have such a relationship, and let us consider the beginning and the end of the this calculation, and we see that we have a continuous linear operator defined on the dense subset. Yes, it is defined on the all step functions. Step functions organize dense subset in L201. Hence, we can uniquely to extend A onto all L201 up to the continuous linear operator. This lemma is proved. Now we will use this lemma in order to discuss integration with respect to integrator as an action of Gaussian-Strong random operator. Let's do this. So the integration with respect to integrators. I suppose that X is an integrator. It has a corresponding representation, so xt now is equal to psi multiply on a indicator of 0t. And now, as we have seen, we can define such a random Gaussian, I will say now functional, because it is related to the integration up to the fixed moment of the time. But of course, after this, we will discuss the changing upper limit. Random Gaussian functional on L201, which is defined as follows. For all h from here, we just put into correspondence integral h dx. Yes. Now what we have to do in order to apply our construction of application of this random functional to random functions, we have to write it into representation. Now it is not hard to do because we just have one summand in this Ito-Wiener representation, and let's check that if h is step function is equal to the sum from k equals 0 to n minus 1 ck indicator tk plus 1, then one can see that integral from 0 to 1 h dx is equal to sum from k equals 0 to n minus 1. We already did this exercise. Ck psi a here applied to indicator of tk plus 1. And then I can continue and say that finally it will be equal to xi multiply on A applied to H. Now it's easy to understand that this representation can be extended to any H, not only such step function, but H which is just arbitrary element of A2, 0, 1. Since then, we understand what is alpha 1. Yes, what is alpha 1 from representation of our random functional. You remember that now we must have the following. The integral from 0, 1 h dx is equal to alpha 0 is absent due to the fact that this is centered random variable, but alpha 1 from h and xi, yeah, where alpha 1 now is from L2 multiplied on L2 to R and is Hilbert-Schmidt bilinear form, but I just recall that it does not it must not to be symmetric. It is just Hilbert-Schmidt bilinear. Okay. So let us find this alpha, and now it's easy to see that alpha 1 h and phi is equal just the product phi multiply h. So this is the linear form generated by the operator A. Yes, and okay, let me emphasize that it is Hilbert-Schmidt with respect to second argument. Only with respect to second argument. This is important, and you can see that it is it holds here. Yeah. So we have such a simple representation of alpha 1, and now one can check integrability of the random functions with respect to our integrator. So now let us apply the general definition. Action on random elements from A2, 0, 1. We will have the following. Let us take functions, for example, eta t. T belongs to 0, 1. Then eta can have an eta-linear expansion. Here is n equals 0 to infinity, and here is, for example, bn psi. There is n time, and we remember that now bn now Bn is a symmetric Hilbert form. Symmetric Hilbert Schmidt form from A2 0 1 n power to 2 into 0 1. We already discussed a lot such expansions, and to define the integral from eta with respect to our integrator, we just proceed as follows. We consider the following. We consider a new form, lambda. Here is dot, here is A of B n. This began to be a Hilbert-Schmidt form of n plus 1 argument, because here we have n arguments, here we have additional one. This is a sign of symmetrization. And let me say that it will be B and with tilde, and I will put here index A. Then the integral from 0 to 1 eta dx is defined as the sum from n equals 0 to infinity b and eta a psi, and here we have n plus 1. Okay, this is the definition of the integral of the random function with respect to integrator. Now let us have an example and consider the properties of this construction. So let us start from the example. Suppose that A is identity operator. Suppose that A is identity. Then what? Then xt is just psi multiply on indicator of 0 t. Let us recall that psi is the formal derivative of w. So this is the integral from 0 to t dw, and it is exactly wt. So we see that when A is identity operator, then x coincides with the Wiener process, and our integral is nothing than extended stochastic integral. Yeah. Okay. This is a good sign because now we understand what to expect from our new definition. We remember the properties of extended stochastic integral. It has some good properties, namely, if the function has random function has stochastic derivative, then it is for sure integrate, and moreover we can estimate the second moment of extended stochastic integral. The same happens there for general case. So let us consider A now arbitrary. This is just element of the set of continuous linear operators in L2, 0, 1. In L2, 0, 1. And now one can consider again the xt, which is just psi. Here is a indicator of 0t. Yeah. Now what we did. Let me write just formally just some formal calculations which will give us an understanding what we already constructed. So when we just have some random functions eta, and we want to integrate eta against dx, we just say that it's like sum k equals 0 1 eta tk delta xtk. Yeah, I just say non-formally. Maybe we expect that such sum will approximate, but and it is like a sum, and I put here psi, and I will put here a from the sum from k equals 0 to n minus 1, and here is eta tk, indicator of tk plus 1, and finally let's mention that this function, random function, is more or less eta. Yeah, when we have a small partition, yeah? Then one can expect that this integral is just a scalar product psi a eta, and it is equal to extended stochastic integral from a eta, from random function to eta. And this is true. So it occurs that integral with respect to the integrator is the already defined stochastic integral, but with respect, but from the new function which is obtained with the help of operator a, which arise in the construction of the integrator. So we have such equality. It can be checked using interlinear expansion directly. Please do this as an exercise. After this, we have good properties. So we have the following properties. If eta has stochastic derivative, then eta belongs to the domain of the integration over dx, and we have the following expectation of eta integral from eta dx is equal to 0. Moreover, we have the equality for the second moment. Expectation of the second moment eta dx square is equal to expectation of norm of eta square. This is norm in L2, So this is still random variable plus trace of A d eta square. Let me recall you again. The d eta is Hilbert-Schmidt. A multiplying Hilbert-Schmidt operator is also Hilbert-Schmidt. Its square is nuclear operator and trace is well defined. And by the way, as we discussed before, this trace can be negative because we have here square. This is not a product of operator on its adjoint. It is square. So it can happen that it is equal to 0 for non-trivial integrand. So we see such good properties, and one can say now, okay, maybe this is just a trivial generalization of the extended stochastic integral with respect to linear process, but it occurs that this construction is very fruitful and very well connected with the new notion which we began to discuss. This is operators of second quantization. This notion comes from physics and is related to Siegel isomorphism between the Gaussian functional and Fock space of boson system with changeable number of particles. We will discuss this further. Now I will give a formal definition firstly, and then we begin to study properties. And only after this, maybe we will see how it arises in physics. But name comes from physics. So keep this name in our purely mathematical considerations. Let me again recall you that we have omega F(E). We have the real separate Hilbert space here. We have psi is a Gaussian white noise. White noise. Noise in H. And finally, we suppose that F is equal to sigma psi. Under this condition, one can say that any random variable alpha, which is square integrable, can be uniquely expressed as an e to n series from n equals 0 to infinity, an psi psi psi. Moreover, we have the following relationship that expectation of alpha squared is equal to the sum from n equals 0 to infinity n factorial norm of n square, where an is the element an is H tensor symmetric part, and n is the norm here. Yeah? From this point of view, one can say that now This space L2 omega Fp, L2 omega Fp is isometric to the orthogonal sum from n equals 0 to infinity square root of n factorial. Here is h and symmetric. Yeah. Why I am saying orthogonal sum? Because we already know that the summands in the e-to-inner expansion are orthogonal. They look like infinity-dimensional generalization of Hermite polynomials, so they are orthogonal. So we have such isometry, and this isometry, by the way, call it Siegel isomorphism. We will discuss it later. But now it is important that in the right-hand side we have purely deterministic Hilbert structure. We have just orthogonal sum of Hilbert spaces. Yeah, and this leads to the following understanding. If we define a linear operator on this structure, then automatically it will lead to some linear operation in this space L2 omega Fp. And the operators of second quantization were constructed exactly in such way. We will begin with this one and then go there. Let's do this. So I will suppose that C belongs to the space of continuous linear operators on H. And moreover, I will choose such C that its operator norm is less or equal than 1. Let me emphasize that this is operator norm, not Hilbert-Schmidt. In case of Hilbert-Schmidt norm, we always put there some index, yeah, related to the number of variables. But now there are no indices, and it is related to the fact that here we have operator. Now let us consider the following transformation. Take some A from take AN. And I will transform this form AN using operator C. I will transform it into the following form: AN C dot, and so on, C dot. I will write it shortly like A with C. Yeah, because this one. More detailing, AN C from phi 1, phi n is equal to AN. Here is C phi 1, C phi 2, C phi n. So, from this detailed formula, you can see the following fact. AN still remains to be symmetric. It's trivial. Yeah. Moreover, AN still remains to be Hilbert-Schmidt. It is less trivial, but also can be checked. Please check this as an exercise. And then I can say that it's belong again to H tensor and C. Moreover, if you calculate, if you not calculate but estimate Hilbert-Schmidt norm of A and C, then you will get the following inequality: A and C norm square n is less or equal than the norm of C into n power multiplied on the norm of A n square. So we even have such a beautiful inequality. Why beautiful? Because we remember that this constant is less or equal than 1. So we have not expanded. We have not expanded transformation in this space, and of course it is linear. Yeah, it is trivial. It is linear. So now let me came back to the space of Gaussian random functions. Yeah? So for alpha, this is the main definition. For alpha, which belongs to A2 omega Fp, and which has following linear expansion. Define the operator of second quantization as follows: gamma C, it is its notation, from alpha is equal to the sum from n equals 0 to infinity. Here is A n C psi. And now, due to this property, we know that this series converge. So we have such a definition of the second quantization related to operator C acting on the variable alpha. Okay, it looks rather complicated, but next time we will see its properties and begin to study it. For today's, that's all. Thank you for your attention. Maybe somebody have questions or comments, please. Okay, if there are no questions, then see you next week. Bye.